So welcome everyone to the Day Talk on internals of database, and I'm Logesh Balasubramanian. So here I'm here to talk about some of the internals of databases, fundamentals of it, and trying to provide some use case on top of it, which we have built our own database for that. I might jump here and there between slides. I might go fast. I might go slow. If you find something which you want me to correct or stop, please feel free to do that. I'm happy with it. So let's get to the next slide. So yeah, this is my doodle, and I already said my name. I'm Logesh Balasubramanian. I'm working as a solution consultant at Sahaj. So I have around like 4 years of experience, all of it in Sahaj. So it's been good time for me. I'm predominantly a backend developer. I've worked a lot on distributed systems. I love working with high scale systems. That's what interests me a lot. And I'm a Rust enthusiast. Like I love developing application in Rust. It really gives me a easier way to solve high scale systems. You don't have to worry too much about the data there because it gives you those things out of the box. And yeah, personal some bit about me. I'm an anime lover. You will see a lot more anime things in my slide. And unfortunately, I'm a RCB fan. And this season we couldn't do much better. Hopefully, next time we will do much. This season is I know I'm in Chennai. This is a hard place to be as a RCB fan, but fine. I have spent around like 10 years surviving school, college, and the work environment being a RCB fan. So I think I can do it. Yeah, cool. So moving to the next thing. So I think the first question that you would have all have in your mind: why do I really need to know the internals of database? I can simply write SQL queries that works, and if it doesn't work, I can put it in Stack Overflow. They will give me some other answers which I can like play with and get it working. Why do I really have to know that? Anyone? I think again disclaimer: this will have a lot of questionnaire in this session. You have to be a lot more vocal. So please feel free to share your opinion. It's completely fine. Any answers? Why do we really need to know? Anyone? Sorry? Two things often we get there. I want to complete complete. There could be a couple of ways to do it. Okay. TV knowing how it works. Right? For my. Okay. Good. Any other answers? Any other perceptions? Yeah. Yeah. If yeah, there are a lot more to it. Okay. It is. How can I stop this? Just click. Okay. This will go out, right? The task. Yes. I just have to wait for it. Is it? Or I have to pull it down. No. The top bit. This one. That one. This will not see. Yeah. Cool. I think it is hidden here, but at least I will give you the statement. Have you heard of this statement, mechanical sympathy? Anyone? I think some of my colleagues will know about that term. We use it a lot in our art. But cool. Thanks for that. That's much better. Still okay. I will close this slide. Cool. Okay. Have you heard of this term, mechanical sympathy? Anyone? No? Cool. Yeah, I know, we know that, but yeah, I got introduced to this term recently, but I was doing it even before. It's a very interesting analogy that someone has come up with. Why it is not? I can't. Okay, it got stuck. Fine. Okay, now it's working. Cool. So there is a quote made by a F1 driver named Jackie Stewards. He said, "You don't need to be an engineer to be a racing driver. You just need to have a mechanical sympathy." What does that mean? Like, what is that mechanical sympathy? So we all drive cars, right? At least bikes, cars, something that you know how to drive. So you would have come up with some assumption saying that like I have to do this to get this done. We all have been doing engine brakes, right? It is not. It is good to do engine brakes in a slopey thing. It's like when we take a overtake, we do reduce our gears if the car is not giving us the throttle, right? Why? Because like inside the gear switch happens and it will not give you the throttle at that point. So you need to come back, which will give you a better throttle. So understanding those things is what he said make him a better driver, because he knows how the vehicle works. So he can use it to the optimal way. But how does it connected to the database? Okay, I was clicking at the thing. Okay, how does it connect to the database? Same thing, like someone said, right? I want to do it efficiently. I want to optimize it to the core. I don't want a mere optimal thing, right? I want to do it in a much better way. And databases are the core of a lot of our applications now. Most of our applications are dependent on databases. That's what the major bottleneck for most of the high scale systems, right? So how does it relate to database? So when you know the internals of database, you can use the pick the right database for your use case, right? You cannot use the same database for every use case. One could be a analytical use case where you can use you cannot use a transaction data store for that. Similarly, one could be what can be one could be a different thing like it can be an unstructured data. You cannot use a structured data or a relational table for such use cases. So you need to understand how it does actually works behind the scene, where to actually put the index, where not to put an index, which index is optimal for this use case, whereas which index is optimal for the other use case. Well, you know the internals of it, it makes you do a better job in what you do. So that's what Jackie also said, like it makes it him better driver if he knows the understanding, if he has the understanding of how the car works behind the scene. Similarly, it makes us a better developer if we know the internals of database. And yeah, disclaimer, database knowledge is subjected to market risk. Please read all database related document thoroughly, because each database has its own implementation of whatever things I want to talk about, because they have taken different trade-off for their use case, which you need to understand when to use what. They have done it for a reason. We need to understand when to use what database. Uh, Again, another disclaimer, I won't be talking about in-memory databases. I will be specifically talking about disk-based databases, and I will be talking about single instance databases. That means I will not cover anything related to distributed systems, or I will not cover anything related to implementing a in-memory database like Redis and whatnot. And the next thing. So for the sake of simplicity, let's assume that we just visualize one table in the database. Okay. Basically, database replicates the same thing for multiple tables. So you can visualize that how a particular table works. Then the same thing will be replicated for the other tables also. Any questions so far? Am I going too fast, too slow? Optimal, right? Cool. Cool. The first anime reference. Let's go. So database file organization. So why do we really need a database? We can simply write it to a file system, right? I just need a persistence. I just need a way to write to something and read it from something that will be persistent. Why do we really need a database? That question is still valid. You can still write it to a file system and you can retrieve it. You can do all those things. Basically, database is just a bunch of files organized in a specific format. It doesn't do anything that you don't do in a basic things, right? In our basic college, we would have like simply opened a file, read from something, right, write it back to Word. That's basically what database do. But they do it in a way it is highly optimized for storage, access, and update. So we will talk about that later. How do they efficiently do it? How do they make sure that access is much more optimal for a particular use case, which they have picked up to solve for? And how do they make sure that they won't use unnecessary storage also for writing a particular record? So most of the databases, if you see, they will have separate files for each table. You can think of it like one file for each table, except one use case or except one database, which is SQLite. How many of you have used it? Why? Anyone have thought about why my SQLite is different from other? There is a term for it. They are called embedded databases. They usually sit with apps. They usually sit with websites. They usually try to sit with the edge devices. So they don't need a very high, they are not meant for handling high scale use cases. They are meant for handling a very specific small use case. That's why they thought like, I don't even need multiple files for it. I just need one file, which I do optimally. That is the use case that they picked and solved it properly. But most of the use case that I am thinking of talking, right, and I have used are on high scale. So most of them actually have single files for each of the table, and also it has separate data files and index files. So what is the data files and data file and index file? We will look into it little later. But why do we really need to separate these two things? I can even store both of them together, right? For a single table, I can have a same data file, same data in a same index and the data in a same file. Why do we need to have a two different things? Any answers? Okay. Okay. Anything else? Exactly. So you won't access every data, right? You have built up like maybe thousands, millions of records in your system. You won't be accessing everything. So let's assume that you index is simply like a registry in a hotel. So I just need to know where my friend is staying in this hotel. I go to the registry, I look at it, and then I say he's staying at room number 301. And that data can be cached. And a lot of people can come and then ask for the data. If it is cached in OS and it is smaller, and if I store it separately, then it solves a lot of problem for me. But if I store it along with the data file, then I have to read the whole data, and then I have to leave out all the unnecessary things, and then I have to fetch the actual data. So that's the reason why database systems prefer to keep index files separately from data files. Moving to the next thing, which is the data file. I already said data files means it stores the data records, which is basically your insert operation with the data, saying that this is my name, full name, whatever, right? Whatever table, columns, and then the rows that you have. That data is sitting in a data file, and there are and there are two major classifications of data files. One is index organized, and another one is heap organized. What are they? Why are they different? So there is a reason, there is a specific trade-off that they have picked up and they have solved it. One is index organized. What does that mean? Index organized means they store the data along with the index. You might think like, hey, you said something here. You said like data files and index files stored separately because for the faster access, blah blah blah. But you said like here it stores together. Yeah, that's true. They solved a different use case again. The use case that they have solved here is they want to have a faster range queries. If the data is getting stored together along with the index, and if I store the data along with the index, I don't need to do a separate disk read. If you look at this one, right, the heap organized, I have to go through this path. I will go from here to here to here based on the query, based on the particular key wherever it exists on the leaf node. And from there, I have to do another disk read to here. That means it's a two disk read form. But if you look at this one, I just have to do the same disk read. I don't have to go to a different place to look for the data. The data is already in the index. But what is the problem with that? Can anyone explain? Because you need more such pages. Because if I can have hundred pointers in a single page here, but I cannot have 100 pointers here because the data is also residing. I will only have 10 pointers. That means I will have more such leaf nodes. Then the disk, the index seek will take more time, but the disk seek will be less. So that's a trade-off that they have solved. One more thing, the sequential reads here, all the leaf nodes will be connected. So if I have to do a range query, I would say like give me all the records between ID 100 and ID 200. All of them will be sitting together from this side to this side. So I can just go to a particular disk pointer and then read everything from the pointer. Say like give me all the thing, and we all know that like disk works with the disk has a pointer or the what do they call needle, which actually goes through the sector or the segment, and we all know that the sequential writes and sequential reads are much faster than the random writes and random reads. So that is the thing that these guys have optimized for. Whereas with this guy, is optimized for a better insertion. So if you look at the insertion here, right, this one is written in a sequential manner. So if I have to do a random write which sits in the middle of this thing, I have to move everything in the middle to the leftmost or the rightmost to fit this particular guy. Then I have to do a lot of disk writes. Whereas this guy will just have to do a single pointer insertion at any point. You don't have to worry about where the data file is sitting. You just have to worry about where I have to point. This is really good for faster insertion, but this is not good for range queries and better reads. So this is a two different way of optimizing what use case that you have. So every time you pick a use case, you need to understand what my reads and writes will be, how I want my reads and writes to be, whether I want a better latency for read, whether I want a better latency for writes. Those are two major things that you have to consider whenever you pick up any databases. Uh, let's move to the next bit, which will also be on the same line as this one, the index files. I already talked about it. Yeah.
So if you go to the previous one, can you give an example of like which database is the organized for the index file?
Okay. That's a nice question. So actually, I think I thought of talking about it maybe in the later, but I will talk about it now. So how many of you have used Postgres? How many of you know which one the Postgres do? Index heap only. And how many of you have used MySQL? Most of you. And MySQL do the first thing. So we all know that, like, okay, MySQL and Postgres, both of them are SQL databases. What is the big thing? I will just use one over the other. Whichever use case I get, I will just use MySQL because I know MySQL better. That's what I have done for Postgres. I've learned my lessons. I'm a very big fan of Postgres, and I have used Postgres for one of the use cases which I will talk about later, where I have burned my own hands and found out that Postgres is not a good fit for that particular use case. So I think thanks for the question, Prasanna.
I have a question.
Yeah.
So in index organized tables, everything is brought up to the memory, and from the memory only the reads are uploaded.
Which one?
For either case, okay, index file it makes the data files are in the disk, so it makes read to the disk.
Yeah.
Whereas in index organized table, doesn't it bring it from the disk to the memory when it is loading the index itself?
Yeah, it will. All this internal nodes will be cached, and even if you do this right, if you go through the disk OS way of doing it, every disk read will go to the OS cache, and then only from the kernel cache it will go to the user cache, and from there it will come to your whatever application that you are using. So yes, it will go through the in-memory flow. Cool. Any other questions on this so far? The data files. Cool. The next one, the index files. I already said, like, why do we need an index? It is for faster selects, and it also gives you an easier way to locate a record in the data. Just like I said, like, I can't go to every room and knock and then see whether it's my friend or not. Okay, that will be very inefficient, right? But if I know the registry is there, and if I can look at the registry, and registry say like he's staying at 301, I don't have to worry about knocking every door. I just go to the 301 and then knock him and then pass. So yeah, that's the whole reason why do we need an index. And there are two types of index. Again, I said clustered index and non-clustered index, and they map to these two things again. So the cluster index is similar to the index organized table, and non-cluster index is similar to the index files thing. So the basic difference here is in clustered index, when you save a data is getting stored in a sorted order. So if you have an index and that index is in some integer or some integer, right? And if you are written 1 to 10, and if you are writing something like 5 again, so it will come back to the middle of it and it will update the file. Okay, so when it updates a file in the middle of it, it has to move everything to the top or bottom. It has to either do arithmetic left or arithmetic right kind of thing. So that's a bigger problem with the cluster index, but it again gives you a better range queries, and it again gives you a better reads. Whereas non-cluster index, it is good for better writes. Again, going to the next thing. Okay, let's get to the next fundamentals of databases. Can you name some data structures that you know that the databases are using and the data structures are powering the databases. B3.
Hashing,
Okay. Hashing. What else?
maybe for heap, we can use the priority queue.
Okay. Binary search tree. Okay. Anything else? Cool. Let's go to. I think there are few things which are unanswered in this thing. I have some surprise for you. Let's go to the next one. This is basically not a data structure, but it's a really important feature which is being implemented in all the databases. I think most of the databases at least. So what is a val? Val means write ahead logging. What is write ahead logging? It's basically up and only file. Whenever a database writes or write means like it can include both insert and update. Whenever database do a write, that means it is changing a state, right? From state 1 to state 2. And what is the biggest thing in database? The ACID principles, right? D stands for durability. The moment the database says like, hey, I have your data saved, that means the data has to be there in the system. Whenever I come back, even if it goes to enormous amount of recovery and failures, it has to have the data. So this is a big, okay. Okay, sorry, I pressed the wrong button. So this is the biggest thing that powers that particular feature. So what is a val? Again, coming back to it, val is basically a up and only file. So up and only file, I think most of you would have done this work, right? Opening a file with a particular mode, read mode, write mode, and append mode. Okay, that's basically this. Opening a file in append mode. What is the big thing with that? When you open a file with append mode, you don't get to edit anything in the file. You can only append to the bottom. What does that mean? That means you can do only sequential writes. There is no way you can do any random writes in that file. So why does it matter? Because again, sequential writes are much faster in disk than random writes. Again, how does the val work? Val, whenever you write a particular entry to the database, it gets added to the val first, and val records are flushed to the data, flushed to the disk, irrespective of how much time it happens. Okay, whereas your writes will not be flushed to the disk every time. It depends. You can set a configuration to do it, but vals are always flushed to the disk for every write. It is not efficient, but it has to be done for the durability. So why do we need to do that? Again, it's for the data integrity and the durability. The moment the database says that I got your request, that means the request has to be there. So how does it work? So whenever database crashes, it comes back, it reads the val file. It won't read anything else. It first goes to the val file, check like, is there any uncommitted data for me? If it is not uncommitted, if it is uncommitted, then I will take it and will try to redo the operation. If it is only committed, then I will go from this state to the other state, say that I am available for the further processing, or else I will keep on processing the data. So that's the whole point of having a val. And again, I said it is most important for recovery process. And again, you all have that question. If I write everything twice to the val and then to the actual data file, will it be using more disk? Yes, honestly, yes. So that's why val will be archived once the changes are committed. So it will have a checkpoint. Once the changes are committed, periodically it will remove unnecessary data. It only keeps the valid data, which it needs for the next recovery cycle. So moving to the next data structure. Is there any questions on this one so far? On val, why do we need it? How is it being implemented?
Yeah. So do we have any diagram for this, like to visualize better?
Actually, on the val I don't have, but for the other data structures I have. But it's because basically a file system with up and only thing. I can have a picture for it, but it will not be a huge picture. Maybe I will try to find something and share it later.
Yeah, please share it on LinkedIn.
Yeah. I think there is a documentation by Postgres. If you just search val internals, right? Postgres has a really good documentation on val. You can read about it. But yeah, I will share about it in my LinkedIn. Cool. So
Okay.
moving to the next thing, which is BR B plus T. Yeah, okay. This is a regex pattern matching. Okay, if you find it, I'm happy. So I think some of you have talked about it. Yes, B-tree is one of the very widely used data structure in databases. What is a B-tree? How does it differ from the binary search tree? So B-tree is basically a generalization of binary tree or a version of the binary search tree, which can have more than two children. If you look at it, it can have multiple children, and it's self-balancing. That means that I don't have to worry about the insertion order. Any order I can insert, it will get into the balance state, so that any of my further inserts or updates or deletes or a select, everything will be O of log n. That's the biggest thing with the B plus tree. And anyone have any idea why B plus tree is very popular? Why not any other tree? Why not RBL tree? RBL or some other trees? Why is it so popular?
Data would be leaf nodes,
Okay. Okay.
And we organize by itself.
Yeah. One. But you have to get into the leaf for that, right? But you can do the same in other binary search trees also, right? Like I'm saying, like even there is a big difference between B tree and B plus tree. I forgot to talk about it. Thanks for pointing it out. So the big difference with B and B plus tree is that in B trees you can have records in the middle of the nodes, middle of the tree. So that means even this nodes can have data records. Whereas on B plus tree, only the read node can have the data records, and then all the internal things are just pointers. And another major thing in B plus tree, all the leaf nodes are connected, so that any of the sequential operation that you do, it will be much faster, because I don't have to go from here to here and here. I can just do 5, 7, 11, 12, 15, 16, 19, 20 in a sequential order. I don't have to worry about any of the random jumps that I have to do. That's the difference between B and B plus tree. But yeah, that's a difference. That's the reason why B plus tree is popular. But why even the B tree? Any idea?
without the rebalancing.
No, rebalancing is that. Rebalancing is one important thing of B-tree, which is why it is also being used. But what are the other reasons? Any other reason that you feel like that could be the reason why it is that? Any guesses? I can wait for some time.
For master access.
Okay, but you can also do that in other search trees, right? That is self-balancing, right? That point is already covered. Like you get a self-balancing that makes sure that the time complexity overlog it. There are other self-balancing trees, right? Why not that over this?
All the leaf nodes are the same thing.
Okay. That is a self-balancing. Again, everything is talking related to self-balancing, right? No idea? Okay, good. I will go. So self-balancing, as it is the first major reason why it is being used, but there are other reasons also. You won't see the B trees being used on in-memory structure, right? You hardly see that. It is very optimized for disk-based storage. The reason is that every node here, it can be a page in OS. It can just be a page in OS, and I can just cache all the internal nodes. For any access I do, it is just O of one access, disk access, because everything else is already sitting in memory. I can just cache all the internal nodes of the B tree or B plus tree, and only the leaf node has to be a disk seek. That means it's just the O of one disk seek for me. It is highly optimized for disk-based thing, where I can have a better read latency. And again, the flexible node structure, when you look at this number, how many branching that it can have, you can define it. If you feel like I need a better branching factor, you can do that. I need a smaller branching factor, you can do that. Whereas on binary search tree, it's always two, right? Again, going back to the, okay. And it supports a range query. Like someone said, I can go to the leaf node, I can traverse the whole thing. Those are the major reasons why I feel like B plus tree is much widely used in the industry. There are a few other things where like it's like Java. It is that it is being used, it is production tested, and it is running. I will continue with it. Uh, so yeah, I don't like Java for it.
So Lokesh, I have one doubt.
Yeah,
Yeah. So you said that this B plus tree stores its node in memory, right?
yeah.
So let's say we have data of 100 GB, and let's say
No, it doesn't store the records in memory. It actually caches the internal thing in memory. All okay. Wait, where is the structure? So if you look at this 20 or all of this thing, it is sitting in disk, but it is cached by OS page. So when you do a seek, it doesn't have to do a disk seek. It is already available in memory because it is cached by the OS. So you don't have to do a disk seek. It is already available in memory, but it is also there in disk. So whenever you do a write, the OS will flush the in-memory page to the disk. Did I answer your question?
so specifically what it actually caches, like the the record or just an hash value of that.
No, the whole page itself will be cached. Like if you look at this structure, right? If you look at this structure, this whole 20, this bar, or this particular node, even this can be cached. Anything can be cached, right? Like it's a OS which takes the decision. For OS, it doesn't matter it's a B-tree node or something else. It's just a disk page. I'm be like consistently being called for, consistently being fetched for. So I will cache it so that I am having a hypothesis that it will be used in further calls also. So it's just a OS optimization. Did I answer your question?
Yeah, okay. I will read about more.
Yeah, good.
Yeah.
Moving to the next one, which is LSM tree. This is how many of you know about one? Okay, I have a really interesting thing to talk about. So this is one of my favorite data structure. I got to know about it in Cassandra. I think we were using Cassandra a lot in my previous project. So Cassandra was using LSM tree. That's how I got to know about LSM tree. But let's understand how LSM tree works. Because whenever I read this, you will all be like, I don't understand anything. I will get into the image part. So whenever a write comes to LSM tree, right, this is how it works. So it goes to the val to make it is persistent, it is durable. So it writes to the var it to make sure that it is persistent, and it writes it to a mem table. Mem table, by the name of it, it means it is in memory. So it have a in memory structure which holds the raters, inserts, and that's all. Whenever you write a thing, it just writes to the in memory and it's persisted through the web, nothing else. So that's why this is much more optimized for write based workloads. So you, because you are just doing one disk write, no index updates, nothing, just disk write, and I'm writing to in memory. You can ask me like, how does it work? What if my system crashes? How does it actually persist the data? That's where the background process comes into the picture. So whenever this mem table, there are multiple parameters. Again, there are time based flushing, or then there are size based flushing. So moment it reaches some defined size, maybe like 100 MB, 200 MB, it flushes it to a disk, and the structure that it flushes is called sorted string table, SS table. So sorted string table, by the name of it, it is in a sorted order. Why? Because it's an immutable thing. I will not touch and update anything, and it is in a sorted manner, and it's again good for range queries, just like how we have seen for the clustered index, right? If it is in a sorted manner, my range queries will be much faster. So same thing here, SS table, I will flush it, but when I flush it, I will keep it in a sorted manner. But when I write it here, it's an in-memory structure. I don't have to keep it in a sorted manner. Even in my in-memory structure, keeping it sorted will not be as hard in terms of latency and throughput as keeping it in disk. Because you know the napkin math, right? In the RAM access in a nanoseconds, whereas the disk access is in a milliseconds or microseconds, sorry. Micro or milli? Microseconds, yeah. So even if you do sorting on the memory, it will be much more faster than sorting in a disk. So whenever they flush it, they keep it sorted, and they also keep the unique data and write it to SS table. Now you can ask me, what if I have multiple entries for a same key? Okay, because one first time when I write it to a mem table, let's assume that it's a first mem table 1. Okay, it has ID for Logesh. Okay, and I come back after a hour, I write it again. I have a new record, I write it again. The new records again goes to a different SS table. Okay, how does that SS table knows that I have to actually check with this one also? So that's where the level comes into the picture, and that's where the compaction also comes into the picture. So the levels, if you look at this, it is ordered in the oldest to the newest. So from the top it is newest, and to the bottom it is oldest. So I want the latest record, I will go through this hierarchical order. I will always check the in-memory structure, which is the latest one that I have. So anyone who have written, it will be stored in the in-memory structure. So I will write it to the in-memory. I will first check the in-memory structure. Once it is not there, I will go to the next level, which is level 0. I will check all the SS tables in the level 0 in the order which is written, and then I will go to the level 1. If it is not there, again I go to the level 2. It is not there, again I will keep on retrying it till I reach the end of it. That's how the read works in LSM. You can tell, yeah, I think from the looks of it, like it's very inefficient. Yes, it is inefficient for reads. There are optimizations which are done on top of it, like Bloom filters and having a separate index for it, but it's a topic for a different day.
Like you were talking about the case where LN, right?
Yeah.
There is ID1, but now I delete the ID. That's the case. So, so I have to update.
Yeah. Okay. Thanks for finding that out. So that's where the next case is. What will happen when I do multiple updates for the same key? I have a key for Logesh, and I'm keep on updating the record again and again and again. That means on LN to the L0, I will have key for Logesh in different files, right? So the key will be from here to here, but the latest one in mem table is going to be the one that I need. All the other things are dead records which I have to clean up, right? Then that's where the compaction comes into the picture. That's where the merge also comes into the picture. So let's look at the name of it. It is log structured merge tree. The log, that means it is append only. So whatever I write here, it's kind of immutable. It's like a log. I will append, I will just keep it, I will not touch it. Even if I have to update it, I will write it here, I will write it in new file, I will not write the old file. There is no in place update, there is only a delete and insert. Okay, so I insert the new file and I delete the old records. So when I delete the old records, I have to remove the old values also, right? Or else I will be just having lots and lots of older data which I don't need, and I will be using unnecessary disk for it. So that's where the compaction comes into the picture. That's where the merge sort also comes into the picture. All of you at least know the merge sort, right? How it works. It takes two things, compares first one, merge it, second one, merge it, and it creates the newer sorted thing, right? So that's how it also works. So it takes two levels. Yeah.
Now is the time.
Sorry. Yeah, I will finish this. Yeah. So if you look at this one, there is a in level 0, there are two sorted tables. One has key 1, key 2, key 3, and same 1, 2, 4. When I merge it, I compare this one and this one, and I know which one is the latest based on the metadata that I have, and I take the latest value here and I will drop the oldest value. How will I drop it? I will not drop particular record, I will drop the whole file. So even if you look at this, I take the key 1, 1 from the second table and key 1, 2 from the second table, key 1, 3 from the first table, key 1, 4 from the second table. I drop both this thing. I won't drop particular part of it, I drop both of it. So now I have a new table which is a merged version of the both the older tables, which has only the latest records or only the unique records. And that's how the leveling works. So level 0 records are merged and move to level 1. Level 1 records are merged and move to level 2. Level 2 records are merged and move to level 3, 4, 5, like that. There are other algorithms for it. This is level based, there is size based, there is time based, and each of it has its own perks. But let's not get into it in this particular session because it is a very different tangent to what I wanted to cover. So I think that's on the okay. Coming back to the actual test I want to talk. So log structure mostly it stores data in hierarchical structure like we see mem table level 0, level 1, level n, and it is optimized for both reads and writes. How is it optimized for reads and write? You say like read sucks, right? Because you have an in-memory structure. If I write and read from it at the moment, the write is already in memory. So a possibility of me going to the level n will be very less. It's an amortized thing. Okay. Again, coming back to it, leverage both in memory and disk-based storage. That's why it is optimized for both reads and writes. Still, I don't agree to the read thing, but yeah, it's really good for writes. Optimized for write heavy because every write it is just getting stored to the memory, nothing going out of that. Only one disk write which is on the val, which you do anyways irrespective of it is B tree or LSM tree, which is there. And as part of the LSM tree, there is no write here, there is a write behind the scene. So for your write operation, it is in a latency of milliseconds, because maybe even better or 1-digit millisecond, whereas on B trees it will be 2-digit milliseconds. That really matters in high scale system. Getting to the questionnaires before moving to here. Do you have any questions on LSM before I move to the comparison?
The compaction part where it does merge and stuff.
Yeah.
So does that happen in the background or when you make the read?
It happens background. All this flush as well as the compaction both are async. So it happens periodically based on some of the parameters that you configure. You can say flush it every 15 minutes or say flush it every 100 MBs or something like that. Similarly, compaction you can say flush it when the dead records are more than this percentage, or flush it once every 30 minutes. There are multiple configurations provided by different databases based on their needs again. But to your question, yes, it's not synchronous. That means this part is only the write to mem table is what you have to worry about. All this part is taken care by the database behind the scene.
Yes, my actual question was when I do the word sort, so I do an L0 and L1.
Yeah.
Does it go back to the L1, L0 or L1?
So I merge all the records on L0, move it to L1. I merge all the records of L1, move it to L3.
So I mean, so L0 is always the latest, basically, right?
Yeah. Any other questions?
Yeah. I have. So just to clarify, right? So suppose in the other case there is a val, it's very simple. So no, I did not ask that. Here, right? Suppose it crashes. I have to go through all the SS tables and look at the val, and that's how I reconstruct the DB, right? Or like
you don't need to. Okay, I think reiterating the question for the people in Zoom. Aniruddha has asked the question like, how does a recovery work in LSM tree? So in LSM tree, what will actually be missing when the system crash? Only the in-memory thing will be missing, right?
yes.
You don't have to worry about any of this thing because it is already immutable. That records are already persisted. I don't even have to worry about all these things. I just have to worry about the mem table. So I will have all the records that I have inserted to mem table. There is a checkpoint on the val saying that from this point I haven't committed. I haven't pushed to the flush to the disk. So from that point, I will write it again, all of them back to the mem table, and I will leave it to the flushing mechanism to take care of the rest. So it will get back to the state it was before when the recovery, when the crash happens. Did I answer your question? Any other question for the people who are in the middle?
Yeah. You said there is no index.
In this, there is no. Okay, again, reiterating for the people who are in the call. The question is like, is there any index in this LSM? How does it work? One thing for the mem table, it is already in a sorted thing. There is a data structure called skip list. You can read about it. That's how the most of the databases actually implement this thing. it is sorted in the way it is already. So it's a kind of an index for the mem table. For the SS tables, most of the implementations have optimizations on top of it. Some of them have index files for each of the SS table. For each SS table, there will be an index file also, so that we can just check the index file just to make sure that whether the record is there or not. And there are even better implementations like Bloom filters. For people who don't know what is Bloom filter is basically a probabilistic data structure which gives you a probability saying that this record can be present. It cannot guarantee you that this will not be there. So the probability is always on the positive side. So it will have false positive, but it will not have false negative. False negative means it will never say that whether when the record is there, it will never say it is not there. But it will always say when the record is not there, it is there. That means it can say a false positive. The only headache is that you will go to the SS table with the empty hand saying that there is no such record. I went into it, I read the whole SS table, but there is no. But that is fine. But there is a positive side to it. Because the probabilistic data structures will just take very small bytes compared to the whole index. Because I will not hold the whole data, I will just hold the probability. It's a different conversation for it, but look into Bloom filters for such thing. Those are the optimizations which are done. So if you look at this slide, most of these things, Apache, Cassandra, RocksDB, I think even Yugabyte DB, I have seen Bloom filters for each of them. So let's get back. So getting back to the differences, when to use LSM, when to use B-tree. I think these are like kind of already bolded for you to read, but I am reiterating it. LSM is known for write intensive workloads, where you have to store a large amount of data and you are using disk and flash drives. Whereas a B-tree, it is a traditional indexing structure which is there for a very long time, and it is very good for reads because you are just doing a direct access. Whereas on LSM, you have to do multiple SS table query to make sure that particular record is there or not. It's an amortized thing. It is all not. It will not give you a O of login kind of a thing. Similarly, for write flow, like I said, it is a in-memory write. It will be much more faster. Similarly, it's an up and only structure. It uses the sequential write, so it will be much more faster. And when to use what? LSM tree are mostly used when you have a large amount of data and it's a write heavy system. Okay, like such as time series databases. Whereas the read intensive workload with a very small to medium data sizes and it's a relational thing, it is much better to use LSM. Let me move this guy. Okay, cool. Moving to the next.
Yeah, Logesh, I have one
Yeah,
query.
please.
Yeah. So, LSM trees are implemented for ALTP database, and the data warehouse type database are using B plus trees.
Yeah,
Can you conclude?
you can classify it. I don't know the exact thing because sometimes people also use it the other way around. Basically, his question is that like is B-tree meant for OLTP workloads, which is transactional workload, whereas LSM is meant for analytical workloads. Yes, kind
No,
of.
actually, I
Yeah.
said it reverse. Like the OLTP is meant for LSM trees or
No. Most of the
OLAP because
OLTP.
Mhm.
Yeah, go ahead, please.
Yeah. Can you show the differences? Like
Yeah, I think if you look at this slide, right, whatever you are seeing, the Postgres, MySQL, these are OLTP data stores. Whereas the other side that you have, I think Cassandra, I won't classify it as OLTP. It's a white column store. Apache HashSpace, yeah, kind of. And Influx is also a time series. Yes, it's a OLAP. RocksDB is a key value store, but all of these guys are using LSM. There are like typical LSM implementation for OLAP, which are columnar also, which is what I would classify as pure OLAP, like Pinot and other things. They have a different implementation of it, but more or less on the LSM thing.
yeah. So databases like Google BigQuery and the GraphDB like Neo4j. So do they internally implement B trees?
Um, I I remember reading that BigQuery is on LSM, if I'm not wrong. I have to re-index my own index. Uh, I don't know. Maybe I have to Google it.
But actually, LSM is for heavy write workloads, right?
Yes.
And BigQuery is for analytical purpose,
Yeah.
as per my understanding. So it should be B tree.
No, it should be LSM. Like you said, right? You said everything. The last word is the opposite of it, right? Like if it is an analytical thing, you do a lot of writes more than reads because you dump a lot of data and you do analytics on top of it. How often you do analytics queries, but you write tons of data to it, right? So it's write heavy more than read. See, even for us, we use Cassandra for one of the analytical use case in the project that I was in. So it is the LSM is meant more on the analytical side. You can, I think there are implementations that also provides. If you look at Gigabyte DB, right, it's basically a distributed SQL database. So it also supports OLTP. So that's why I won't classify these things to the OLTP and OLAP world because that classification is completely for a different side. It's on the access level, whereas this one is on the implementation level.
Okay, Logesh.
Yeah, good. Moving to the next thing. Are you ready to apply the knowledge? Again, my favorite guy, Goku. Are you all ready or should I wait for some questions?
How is the Elasticsearch a database?
How is that a LSM implementation?
How is it a database? Search system?
No, it's a search system. It provides the indexing, the reverse indexing, but you can also use it for other purposes.
So a database is encoded inside an Elasticsearch.
No, they provide a indexing which actually do the reverse index. So data is stored as it is, data files and index files, right? What is the index? That index is a reverse index. So you will have an index for each word which points to the document in Elasticsearch. So that is the index for that thing. So in Elasticsearch, what you usually do is like I type something, give me all the suggestions for it, right? What are all the things that has this word? It's basically a reverse index. I have a text. What are the documents that have my text? Okay, it's basically like a key is the word for it. Okay, there is nothing much there. So that's the thing here. Again, moving to the next bit. This is the most interesting bit for me. I will move this guy. Okay, cool. Okay, going back to the project I worked on for some time. It's interesting to talk about it here. So I was working in this project for around 3 years now. I moved out of it now. But this is a very interesting use case. I solved that. So I think the domain that we were in is on the connected vehicle platform. We were working with one of the car manufacturer. Instead of getting into the what we developed for them, I will get into the what use case which this particular talks is on. So there was a use case where vehicle will send stream of data. So connected vehicle means they have a SIM on it. They can send the telemetry data to the server. So they send the telemetry data to our backend server. They just stream it whenever they generate data based on the sensor that they have, based on like data like whether the door is open or not, what acceleration that I meant, whether the pedal is pressed or not, what gear I'm using, all those informations. So those sensors will be captured and will be forwarded to the backend system, and the backend system has tons of business use case built on top of it. One of the use case actually uh, we had to keep the latest record that we get from the vehicle. So that means there is a stream of data. At every point, I need to know what is the latest record that I got from the vehicle. So basically, we listen to all the stream of vehicles data and we put it to a database. And the structure is like this: we have a vehicle ID and the latest value. It's kind of a JSON. That's why I put it. It has a lot of sensor values, and we were using Postgres for it. That was a mistake I said. So everything worked well till the morning where our database was down, the entire application was down. The major reason is that it was a Monday morning. The interesting thing is that everyone wants to go to office and use the car on Monday morning, right? Because like how many of you go to office on Monday? prefer to go to office on Monday. Monday. At least we do come. I know how many people, but at least like if you are going to office, not that's a different thing. But at least, so very interesting thing. One of the Monday there was a huge peak of load where we were inserting around 20,000 records every second, and our IOPS load was just 15,000. We were not able to handle that load, and our system crashed. We couldn't find out how to fix it because a load is coming in. All like we could do is increase the IOPS. We did that and it eventually fixed it, but we know that the problem will come on any day because the car manufacturer was selling more such cars, and our prediction was 10x vehicles in the next year. So we had to support this use case much better in upcoming months. We can't wait for it. That's where the request comes to have a better solution for this use case. What can we do about it? Any solutions? Anyone have any rough idea what you could have done? Some of the people are sitting here.
See, typically for the database practice from a data perspective, we recommend highly fluctuating load balancer.
We did all those tests. If you look at this, we have replicas. But the problem is that our IOPS is hit at the peak. That means that in the whole cluster, I can't write anymore because my disk cannot handle more than that. I'm getting huge load of data, but I can't insert because I don't have the bandwidth for it. I don't have the throughput for it. So
the issue there is storage.
Because this writes are failing, because the database is already overrun with the existing writes.
So when the writes are flying, then you cluster the database. High availability architecture needs.
So yeah,
in the middleware and in the database, so that the data comes to the database, so that the system does not fail.
so you can go to a distributed systems which can handle parallel writes, right, on multiple systems, not just on a single master server thing. You can have multi-master or multiple things which are listening for the writes. Okay, like I said, the one that we were using, the Postgres, which was not in a high availability mode in terms of multi-master thing. So we were not having partitions. We just had a single partition which is just replicated to the different ACs, and just for the availability purpose. It is not for the throughput purpose. Okay. So I think let's get into the actual problem with Postgres. Why is it not? So let's understand how Postgres works to understand what's the problem that we face. So in Postgres, when you do update, it's not actual in place update. It is actually a delete and insert. For deleting the record, it also puts a one more entry called tombstone, saying that this record has to be deleted, and it also writes a new record to it. Since it's a JSON data and a huge data, it can't fit into the page. It puts it in something called toast. Postgres has something called toast, which is kind of a heap, which doesn't have a page structure optimized for reads and writes. So we were unaware of all these things. We did like, okay, Postgres is working, why can't we just use it? We started with a very small number of vehicles, so it scaled for a very long time. For 2 years, it was working properly. We didn't have any issues. One fine morning, we had this issue. That's when we understood, like, okay, I do 20,000 records insert. That means that I have to delete 20 more records now. I have to do 20K writes now, plus another 20K writes for deleting the older records, because that disk has to be cleaned up, right? Someone has to go back and then delete, do the thing. There is a process called auto vacuum in Postgres, which actually do the vacuuming thing, like removing unnecessary dust out of the system. This is the way the Postgres works. Anyone have question here? But you all understood what's the problem with this, right?
So should we use Postgres or not?
Okay, that's a good question. Again, it's specific to the use case. So Postgres has a really good optimization called HOT, which is update in tuple or something like that. You can read about it, which makes so that it updates the same page instead of writing to the different page. It leaves out some page size for such updates to come, so that whenever such, if it just writes to 60% of the page and keeps 40% remaining for such updates to come. So whenever such updates come, it will use the remaining space just for the updates. But those are optimizations. By default, you won't get it. You have to enable it. So we didn't use it. The way we solved it is we moved to Redis in a high availability in a multi-partition setup. The reason we want is there is an additional catch here. So when if I go back to here, right, if you look at it, there is a specific thing in a car where there is a protocol which says whenever a car goes out of the network and comes back, it has to send the latest data first, not the old data in a message order. That means it is there to make sure that if a car crashes, it has to send the crash data first, not the older data. It is for the safety purpose enforced by the protocols. But that is the problem for us because we want the message order to know what is the latest data. There is no such way. We have to handle it ourselves. So that's when what we did, we read the latest record from the database and then we compare the timestamp saying, is this latest in the record that I have on the database or not? If it is, I will write it. If not, I will discard it. So that's how this one was implemented. So if you look at it, it is 20k reads plus 20k writes plus 20k deletes. So that many IOPS that we were using, and our system just cried. So we moved to a Redis cluster for trade. We traded off consistency for latency because it's a stream of data, and our clients are fine with having outdated data for a very short time. Because anyways, I will be updated with the next latest data because a stream of data is coming in. If I miss one update, that's fine for them. So that's the use case that we had, and we looked into it. We thought, why can't I use an in-memory structure, which is very optimized for both reads and writes, right? Because in memory, like I said, it is much faster for both reads and writes than disk on any given day. So that's what we did. We moved from Postgres to Redis, but that's not where it stops. So we took it, we thought like, what, there is no other option for us to have a better approach, but the persistence is also supported. We looked into it, there are options available, but we thought like, why can't we write one on our own? Okay. So that's when we actually came up with the internal hackathon for around 2 months, where we asked every one of our employee to pick up this problem statement and create their own database which could solve this problem. There are few constraints. Like I said, there are heavy reads and writes operations. Both reads and writes has to be considered, and the persistence should also be there. Those are the two main things, and it's also update. It's kind of a key value store. So that is the basic use case. They took it, they wrapped into a different use case, and then added some more constraints to make it interesting. That's where this one comes. Just give me a second. Any questions at this point till now? Can I go to the next phase of the session? We can be used. We do have message broker. This part is message broker. Okay. This part is all message broker. But how do I know what is the latest data in the message broker?
I mean, this, the database is loaded with a lot of data, right?
Yeah.
Right. So we can
the
flow rate.
That back pressure is already there. So this one crashed, but after that we fixed it. This back pressure was there. So if I can't consume it, I won't consume it at this speed. If this consumption is slow, this consumption will also be slow. But the problem for our client is they open an app, it is giving 30 minutes old data, and the users will be frustrated, right? You are using your car and then you're opening your app, it has 30 minutes old data, which they are not happy with. So that's when we moved to Redis and fixed it. But coming to the hackathon thing that we did, so there are few constraints which are something I picked up and try to use it to my solution to get the better solution. So I participated in the hackathon, and these are the various things that I would say it's important pieces in the problem statement. So one thing they have points only for writes, not for the reads. Though the use case actually has both reads and writes at the same level. And there is no time limit for system recovery. It can take infinite time to get recovered. There is no time limit. This is an additional thing which they did just to make it interesting. In a real world scenario, this is not possible. And another point is you can have additional point for durability. This point is very high such that it forces everyone to do persistence. And they said like you will get NVMe SSD in test environment. Whenever we deploy it, there is an NVMe SSD. That means it is really good even for random writes and random reads. Compared to hard disk, which is terrible for it, this one can give considerable performance for random writes and random reads. And there is a variable payload size. Why does it matter? I can have any size of payload, right? It matters because if you have a variable payload, right, I can't do in place update. If I have a first package of size 100 KB and next package of size 150 KB, I can't write 150 KB data in a 100 KB size. I can't do in place update. I have to write it somewhere else and delete the record, right? Same way, I have a 100 KB data sitting there and I have 80 KB data coming in. There's a 20 KB which is missed in. It's an internal fragmentation for the particular page. So then I have to have a different process that goes and reads, remove the internal fragmentation, come back, give me back the data, give me back the size, sorry. So that's additional constraint which enforces us to go with the append only thing or new insert and delete approach. So let's get into the design choice which I made. So B-trees, like I said, it is optimized for reads, but it sucks for writes. Similarly, LSM is good for writes. You all would have thought like, okay, you would have gone with the write LSM because it's write intensive. I didn't do that. I looked into it. I thought I can take a even better approach, which is a mixture of both B-tree and LSM. Can I combine these two and then get a better approach, which is good for both reads and writes? There is a catch here. This records, how many records that get inserted is on the, there is a limit for it. I didn't put it here, but there was a limit on how many records that they can ingest to the system. Okay. And they also give a size of the RAM that we get for the database to be deployed. So when I calculated it, the size of the RAM, I can easily hold the index in memory. So that's when I took a call. Okay, before going there, why I didn't choose the LSM? There is a bit there. So in LSM, if you look at it, I have to write it to a val to make it durable, right? And then I also have to, in the async process, I have to take the mem table, write it back to the disk. There are two disk operations which are happening, be it async or sync. Together it is two operations. I thought like, why can't I merge this two into one? Can I do much better than this? Okay, that's where my approach comes. So it has an in-memory index and the append only files. So I thought val is already holding my record. Why do I need to have a different structure which holds the same record? I will not even delete my val record. I will just keep it, which already has my record. I just need an index which says where in my val the record actually resides. And I felt that I can keep it in memory to make sure that it's just one disk seek and disk write for both reads and writes. If you look at the read flow R1 and R2, it goes to the in-memory index. It checks whether the particular key is present or not in my system. And if it is present, the key value, it looks like this. It holds the file ID, whatever the name of the file, and the offset where that resides, and the size of it, how much I have to read from the offset, and what is the timestamp. So this timestamp is needed when I do an update later. I can compare this with the latest data coming to see whether it's the latest data or not. So these three details are more than enough for me to go to any file, read something, and then give it back. Like I said, NVMe SSDs are good for random reads also. The performance that NVMe SSD provides is much better for random reads. So I thought I will just do basic what Postgres do. Like this part was disk in Postgres. I moved it to in-memory. This bit was, I think, for the people in the Zoom. This bit, the in-memory index was also on disk in Postgres. I thought I will move that also here. that will make all my disk seek just to one. So, and when I write it just to the active files, just like how it was on LSM. Okay, I will have some set of open files. I will just append to that file. I will not do any in place operation. Once I reach the limit, I will move to read only operation. Sorry, read only data files. Once that is moved, I have my own heuristics and metrics which takes and do compaction. Which takes the read only data, do compaction and gives it back. So you can ask like, hey, this is again 1 plus 1. Yes, but if you consider that, then it is 2 plus 1 in LSM. If you consider compaction also into the disk access. So yeah, this is the design that I have. So if you go to the read path, again, like I said, if it will check whether the ID is present in the index or not. If it is present, it will take the file ID, offset and size. With that details, it is more than enough to query any file system and get any data that you want. And I deserialize the byte to object and return it back. And there is a write path, which is I get a data, I serialize it, I write it to one of the open file, update the index saying that this is where my new record is, and my job is done. Coming to the compaction part, which we have talked before, again the same thing, the way it happens. So it takes multiple records, it do merge sort, and then it puts a new record, deletes the old record. That's how the compaction works. But the way I have done it in my system, there are two metrics which I look for. Not metrics, but two things, two constraints are kind of. One is every minute I check for compaction, whether I have to do compaction or not. And the way I will check it is, I will see whether the overall disk date record percentage is greater than 50 or not. What is the worst case thing? What is the best? So let's assume this. If my system don't even have date records, I don't even have to do a compaction, right? Because all of my data is correct. It is needed. I don't even need to delete the records. So that's why whenever I write, I also make sure that I have missed one record that has to be deleted. I hold a counter which says how many records has to be deleted at any given time. That gives me a vision or idea. There is a question in the chat. Is anyone looking at the question? Which one? All the questions, is it? Okay. Sorry, I think it is mentioned that all the questions in the chat, we will go over it later. Sorry for that. So I think again the heuristics, right? Coming back to it. What is the worst case thing? Which is I compact unnecessary data, which I don't want to do. That's where I put this thing 50%. That means when I compact, I'm gonna get better than 50. That means there are 50% worst data, 50% best data. I will keep only the new data. Sorry, not worst and best, old and new. So I will only keep the new data and I get 50% of feedback. So if I do 60-40, I have to rewrite. Like, why you can ask me like, why is it 50? Why can't it be 40? Why can't it be 30? Something else. If it is 30, that means only 30% of my data is bad. But for that, I'm rewriting 70% of data. But if I go with 50, 50% of data is worse. That means that I have to delete it. And when I do it, I'm gonna do only 49 or something like that. So that is always optimal. So that's a heuristic I got, and this is the process that I did. So whenever I do a compaction, create new files for writing, close all the open files so that it will be available for compaction, iterate through the records in index instead of going through the SS table like how LSM do. I went through the index because for me index is an in-memory seek. I don't have to worry about disk hole seek. I went through all the index, take all the records and write it back to the new files. Again, this is random reads for me, but I'm fine with it because it was NAME. So this is how it works. Once all the records have been moved, that means I have moved all my old records, merged them, only kept the new records in the separate files. I will delete the older files. That's how the compaction I have designed work. Any question till this point?
Why not more than? I get why less.
No, think about it, right? So that's what, if it is greater than 60, then I have a probability that if I can see, my thought process is like, I only want to do a efficient one. What is the efficient one? 50-50. Anything over 50 is efficient because I'm going to write less record, delete more record, right? I can go for 60, 70, 80. But the problem is that then I will be keeping lot more older records in my system. Then it's a huge process for my compaction to happen. So it is better to do smaller compactions. If you have run Cassandra, I think Preeti knows about it. Smaller compactions are much faster, much better than running a whole long, bigger compactions. Moving to the concurrency primitives. How many of you know about what is concurrency primitive? What are the concurrency primitives? Cool. At least let's go to let's understand what is concurrency. At least people understand what is concurrency, right? I have multiple threads. I want to do a process. I want to process multiple things concurrently. That means simultaneously at the same time. Not at the same time, but in a timeline, I want to do multiple things concurrently. Concurrency and parallel things are two different things. Parallel means that I will do in parallel, whereas concurrency means that I do one after another kind of a tiles kind of a thing. So concurrency lets you utilize your system to the fullest. Like you have multiple threads, you can perform multiple tasks, one waiting, one doing something. You can mismatch such, or you can pick and do multiple tasks utilizing the CPU to the fullest. That's what concurrency is, and it is very essential for performance and responsiveness, and specifically resource utilization, which is your CPU time. And let's come to the concurrency primitive. So concurrency primitive are your mutex logs, all the ways of getting the thread safety. It's basically a name given to the list of whole umbrella of things, which is low-level construct that helps manage and synchronize concurrent execution and ensures data thread safety. But basically, it is your mutex, semaphore, message passing, atomic operations, all those things. It's a whole umbrella term given to the data safety mechanism for in concurrent world. Okay, so why does it even matter? In every database, you do parallel reads and writes. What are the basic things? You don't want one read to affect the other read. You don't want your one read to wait for the other read to finish, right? You don't want some other keys write to block your read. I am updating Logesh, but why should Aniji's update has to make me wait for it? I am a different key. I don't even have to wait for it. I am living in my own universe. I don't have to worry about it. That's like a pure concurrency, right? Key level concurrency. I can do writes for multiple keys in parallel. I can also do reads and writes in parallel. So that's a basic thing. And we all have seen most of the databases that you are seeing, they do mutex logs. Some of them do copy on write, which are much better version, but it takes more disk access. But I have gone with a different approach. So, okay, I didn't go through this question, but what do you feel about this? Which one is the best among the concurrency primitives that you have used? I think most of you would have used some logs, right? Mutex, read write logs are much better than mutex because you can separate read and write paths separately, right? Reads can happen in parallel, whereas when write happens, it will block all the reads and writes. Whereas multiple reads can happen at the same time. So that's a optimized version of mutex. Similarly, message passing is there, semaphore is there, and atomic operation. There are tons of other things. I have written a blog about it. You can find it in my website on what are those things, but going to it. So I felt that having no lock in the system is much better than anything else because your CPU time is much faster than your disk access, and you make your CPU wait for something That is the worst thing that you can do to a system. If you want to achieve the entire capacity or the throughput of your system, you have to make sure that you don't make anything wait for something. So it is a bit hard to achieve, but I have done multiple things to make sure that I can arrive at that solution. One interesting thing, one of my colleagues did the similar kind of a design. It was a coincidence, honestly speaking. The same design in memory structure, up and only file. There is a database called Bitcache, which is based on this design. So we both referred it. We felt that it is much better than this. We implemented it, but he did through, interestingly, he also did it in Rust. He also used the ActiveWave framework which I use. So it's not a language which gave the performance. It's not the framework which gave the performance. It's actually the primitives which gave the performance. So I did it using Locktree. He did it using Locked, and my solution was 20% to 20 to 30% better than his. And when we looked into the performance of the database, when we did the load test, his system was not utilizing the CPU to the fullest. It was stuck at 40% and 50% of usage, but the throughput is gone. Mine was at 98, 99% of CPU, and that's the max throughput that I can get. If I want to go even better than that, I need to go for a better design. I can't do anything with the concurrency primitive anymore. So the way I have implemented is, so if you look at it, there is an in-memory structure, which is basically a hash map. And if you are in a Java world, you know that there is a concurrent hash map, which gives you the concurrent way of accessing a hash map. I use something called dash map in Rust, which actually takes the concurrent hash map implementation in Java, but do it without locking. So the way they have done it is using atomic operations. There is an operation called CAS, compare and swap. So it basically works optimally. It's not a pessimistic lock, it's an optimistic lock. So what is pessimistic? What is optimistic? Pessimistic means I lock it irrespective of whether this could be accessed in parallel or not. I don't even know whether I need it or not, but irrespective of it, I will lock it. Whereas optimistic, I will try to update it. But if I find it like at the last moment, this is being accessed by someone else, I will come back. I will revert. So the way it works is, there is a compare and swap. So I say, change this value from 1 to 2. It will change only when the value is 1. If the value is changed to 1 to 3 by someone else, it will revert back. And then say like someone else changed it, your transaction failed. So that's a hardware level thing being provided by a lot of our chips. There is a CAS operation being provided. Like if you write assembly code, right? There is a CAS operation provided by your chipset itself that do this at the assembly level. There are like it was first in software level, and people find it like this. If this is implemented in hardware, it will be much more efficient. That's how we move to the hardware level. So the one that exists here, it uses a hardware level CAS operation, which do the atomic writes. So all the atomic integers that you are seeing, right, in all the language implementation, they are based on the CAS operation. It actually takes the old data and the new data, and it compares the current data with the old data. Only then it will update the new data, or else it will come back and reprocess it. Okay, so my index updates are now lock free. What is the next thing? Now I have a disk write. I have to write it to the disk. I have a file handler for the disk. And in Rust, the beautiful Rust won't let you have the same pointer by more than one thread. If it is a mutable thing, only one thread can hold access to the pointer, so that no one else can access the or update the pointer in parallel universe. Okay, that's the way Rust works. So the way I have did it, there is a concept called message passing, and the Actis framework that I use is built on something called Actors. They provide something called Actors, which is basically a programming model altogether, like object-oriented, functional, right? Actors is also a different programming model. It's all act like a message passing thing. From actor A, I pass a message to actor B. All of our networking, right? The SIM that we are using, all of them are based on Erlang, which is based on actor based. That's how they make sure that highly concurrent mobile usage is happening. So that is the actor. Note it down. You can read about it later. But I use message passing and actor while writing to the disk. So when you go back to the first piece here, so whenever the disk writer picks something, it picks a random one out of the active files, and there are actors receiving message for each of the file. So basically, it's like one thread for a particular file. That thread doesn't have to worry about someone else accessing the file at the same time because he is the only writer. And the way the thread gets notified is through actors. Actors will be fed with messages that the frameworks will take care of. That message passing is happening through the message passing thing that you get on threads and process. So that is the way that I have handled the write part. So all my writes no longer go through the locking. So it just goes to the disk writer. Disk writer picks up one of the open file. It just puts a message, hey, insert it to the actor, and it will wait for the message to come back from the actor. The moment it gets the message back from the actor, it tells the client, hey, I have your data ready. So that's how the write works. So then there is a read. So the interesting bit that you have, the basic read that any of your system that you're using, you cannot have two different reads on the same file handler. You open a file in a read mode, you will get a file handler, right? Whatever variable that you are getting out of it, it's a file handler. That file handler will not be used for multiple reads at the same time. That's the implementation thing. So there is a better version of it called preread, which is parallel read, whereas in Rust it is read exact at, which internally use a preread in C, which internally use a different kernel level thing. So I made sure that I can read from the same file in parallel. So this part is also not blocking. My read is not blocking. My write is not blocking. My index is not blocking. What is the next thing? I have append only file handler so that I don't have to worry about parallel reads. Okay, yeah, this bit is a bit different. So I had a different file handler for reads and writes. So I open the same file in a read mode and I open the same file in append mode so that I don't have to use the same file handler for both reads and writes. So yeah, it's a bit tricky, but try to understand the bit. And for the metrics, I use atomic integers again. That will make sure that this is also not blocking. Any questions here?
Logesh, yeah.
Yeah.
Should
Yeah,
I
please go ahead.
should I ask?
Yeah, please feel free to ask.
Yeah. So in the fourth line, you said use different read only and append only file handler for parallel read and write to same file.
Yeah.
So when a system access any file, it's lock that file, right? So
It doesn't.
can we parallelly do read and write?
It doesn't. There is no lock concept for a file. You have to put it on your application level. If you want that file should not be accessed by someone else. So I think some of these folks have tried it in their training process. Like someone tried to access this right to the same file that was reading. It will not give you those options out of the box. You have to enforce it at the application level. You can have a read and write handler for the same file at any given time.
Yeah, but actually in operating system there is a concept how this process or any thread executes. It logs the resources. So this is what I am relating to it. So let's say there is a.
So OS doesn't give you those functionalities out of the box. It is the application that provides it. You can ask the OS to give the functionality, which I didn't. Which I said, like, my system will take care of it. I know what I'm doing. Give me the access.
Okay, Logesh, thank you.
Yeah. Okay. Next thing, which is the interesting thing I said, database recovery flow. So in my design, only the in-memory index has to be recovered. Like how in LSM, only the in-memory part has to be recovered, right? Similarly, in my design, only the in-memory index has to be recovered. Since there was no limit on the recovery time, I took my whole long time to read all the files in parallel, index the latest record based on the timestamp, and throw away the rest of the records. Because there was no limit on it, I took all the time. But ideally, in real world, what you can do, you can have checkpoints and snapshots for the index, and post the snapshot, you can actually update the index and like restore back to the index, and then post that you can read and then update the index. That's how some of the in-memory databases work. And one more optimization there, I did buffer reader to speed up the read process. Why I didn't do the buffer reader for the actual read flow? What is a buffer reader? Any guesses?
Can you read parts of the I did or flush it out? Like you don't read everything in one go, you read it in parts.
Yeah, basically what buffer reader do is you request the index 0, it takes, and then the buffer size is 100 KB, something like that. It takes a 100 KB from the disk, put it in the buffer, and while you are reading it, it takes the next 100 KB from the disk, keep it in the buffer, so that you can do the next read. So it's like kind of a hack that they did, or it's not a hack, it's a optimization that they did to fetch the next record while you are processing this record. It's similar to how CPU this thing works. What is that? Pipelining. Yeah. So that's how buffer reader works. But why I didn't do that for the actual reads?
Based on events.
Exactly. I'm doing random reads. I don't even know whether I need the next bit or not. Whereas here I'm reading the whole file from 0 to the end of the thing. Okay, I damn sure know that I need the next bit. So that's why I use buffer readers to fetch the next record while I'm processing the current record. Whereas in the actual read flow, I went with the basic read. That's a bit on database recovery. And okay, before getting into the conclusion bit, any questions on the database that I have to say?
Comparison. This said,
I didn't do it, but there was RocksDB implementation by Yogi and I beat it. So I know that like somewhere it is better than that. But the thing is that some of the optimization that I have done, I didn't include it here. That won't fit for it because there are specific to the use case that we were solving. Like I did a very custom encoding for us because the data, I know the data, so I did a custom encoding for it. But that won't work for every use case because they were written for a general purpose thing, right? So that's why I didn't compare it with the actual thing. But I'm thinking of writing a I think RocksDB actually expose an API, right? Like RocksDB is very popular because they actually expose an API which anyone can plug in and then use it. So lot of engines have plugged in RocksDB and used it. So I wanted to implement the same interface and try to compare it, but I couldn't get time to do that. But yeah, that's a nice question. I'm where I stand. Yeah.
So this database works only on SSDs, not
I think most of the SSDs are very cheaper, man. We rarely run databases on hard disk. Do you really are people really running databases on hard disk now? I think Amazon have moved out. They still provide GPT-2 and GPT-3 support, but they are also SSDs.
But it will still work, right? On a hard disk.
It works, but it will be slow. It is not meant for that. Any other questions? Anyone in the chat before I finish it? Yeah.
The problem is that why the variable payload size
Matters, is it? Why does it matter? So the question is that like why does variable payload size matter? So the thing is that like that's what I said, right? You have a different size record. The first key, the record size was 100 KB. Second one is 150 KB. If I do in place update, I don't have a space for 150. I only have 100 KB because the rest of the things are taken by the other records. So I have a page. Page will have multiple records. Page is like a page in a OS. Okay. Let's assume the file. Okay. 0 to 100 index. Let's assume that one index means 1 KB. Okay. 0 to 100 index. I have written first record. 100 to 250. I have written the second record. 250 to 500. I have written third. Okay. Now for the second record, I got a 500 KB next payload. What will I do? I don't have the space in this time. I have to move the whole thing out, put the space for this, and then I have to do the in-place update, which is very inefficient. Postgres doesn't do that. Postgres do append only thing. Postgres also provide MVCC, which is not included in this call. I think answering to the question, they do it for a reason. They provide multi-version concurrency control. You can revert back to any version in Postgres. So just like how we do on Google Docs and other things, right? You can go back to different version of the data and restore from that. For every key, do that. So it is there for a reason. It keeps multiple records for a reason. So even if you look at this one, if you look at it, the next version, it has a next version index pointer, right? The older version is having a pointer to the newer version. This is bit of the multi-version implementation. So the index will have the newer record, but you can go back to the older record also. If the database decides like the newer record is crashed, it's not yet committed, the transaction aborted, it can go back from here to here because it keeps the older record also. So they do it for a reason. Again, I'm saying every database have done something for a reason. Learn about it and use it well. So that is my next bit of thing. There is no one fit for all, but there is one hack here. Now Postgres is putting themselves as one fit for all. They have enough plugins to plug to make it an analytic database, make it a vector database, make it a graph database, make it a geospatial database. They have all those extensions, but still I feel like they are not that great compared to picking a database which is specifically done for that purpose. They always provide a better performance. And like I said, right, I think Prasanna asked that question. Postgres and MySQL are not same. For us, it looks like they both are SQL databases. From the internal aspect, one is cluster index, one is non-cluster index. One do in-place update, other do insert and delete. So that is the first point. Second, these are all the parameters that we might have to look when you are getting any use case, whether it is OLTP or OLTP or AP or structure on structure, row based, column based, white column based. What do I have to do? Read optimize, write optimize. What is my read flow? What is my write flow? Whether I want better reads or whether I want better writes. So everything you have to consider. You need to understand the implementation of each of your databases, and then you have to make a call. So yes, it depends. It depends. Like the disclaimer I said, everything is subjected to database implementation. Read about the implementation. Read about the documentation. It helps. So yeah, thanks. This is my LinkedIn ID, and I have my own website where I share a lot of this knowledge. I have written few things about databases, and I'm a big fan of ScyllaDB. If you don't know about ScyllaDB, read about it. And this is a database internal Discord server that I follow. It's I think it's a very big community, and it's a world-long thing. People from different places of the world are there, and who are there are the people who wrote the database internals book and other great people who have developed these databases. So you can go there, listen to that conversations. It's a very enlightening thing. And yeah, please share your feedback. If you find anything that could be improved, anything that we should continue, anything that could be plus minus things, you can put it here. We will read about it. We will change it next time. Thanks. Okay. How do I check the messages? Can someone read it? Is anyone looking at the messages? Okay, we will share the presentation to you somehow. You can check my. Yeah, we will add it on a meetup, but people who didn't sign up through the meetup directly went to the Zoom. I will post it at least either on in my handle or somewhere else, in the website or in the handle. Cool. Thanks. Any questions? Any discussion aspects?
Hi, Logesh.
Yeah.
One last personal question.
Yep.
How did you master this much of database? Because before joining this session, I was just like backend developer बनना है तो SQL का query मारना आना चाहिए और database कैसे connect करना.
Okay. So I think to answer your question, I was fortunate enough to put in such places to the situation forced me to do that more than I end up doing it on my own. So it was subjective again. At least that's what I do. I think I felt like not everyone will get this opportunity. What if I share my knowledge to people? They can learn from from the mistakes I made. That's where I am. I don't know the answer for you for your question. It depends again. It's a situation that I got into.
So you have any roadmap of any resources path like we should follow to master like you have done?
So there is a very interesting book on database internals. The name itself is Database Internals. You can read about it. It's a very interesting book. That's the book that I referred before implementing it. Whenever I get into this view, this particular Discord channel is also run by those people. So it's a thing that I would say you can refer. Sorry, author. I think there is only one book in there. I don't know the actual author name. Somewhere in Alexa, I don't. Yeah.
Designing data.
Yeah. One more thing, there is another book on this called Designing Data Intensive Application DDIA. It's also very popular. These two books I would definitely refer if you want to become a better backend developer. Cool. Thanks everyone. Yeah. Please go.
Hi, Logesh. Yeah, one last question.
Yeah.
So do we have to specifically learn any language like I know only Python? So can I implement features like this?
You can do it on Python, but I think it has Python is for a particular reason. Just like the databases, the languages are also there for a reason. Python is not a system level language. It's an application language which is meant for having a better iteration while you are developing. You get to develop lot more faster in Python, but it comes with lot of abstraction. That abstraction kills your performance.
Okay.
So you want to develop a database, there you have to pick up any of the system level programming languages like C, C++, Rust. I think even to a point Go is also good.
So for handling the telemetry data, we should use like languages like Rust and.
No. We use actually Java for that because that's an application that we have built. All of our scale was handled by the database and the distributed systems like Kafka, Cassandra, all those things. Those are implemented in different languages. To your surprise, both of them are implemented in Java. That's the reason I hate both of them. There are better versions of it. Cassandra Scylla is a better version, which is rewritten of Cassandra in C++. Similarly, for Kafka, there is something called Red Panda, which actually provides a C++ implementation of Kafka, which is not yet picked up the pace like Scylla, but it is really good. But like you said, we don't have to use those languages to implement high-scale systems because the thing is that there are trade-offs that you have to make. The biggest trade-off that you have to make is about development efficiency more than the scale. So you can still do the same thing in Java also, like how people have done it for Cassandra and Kafka. But the good thing with Java is that it is very big community, it is widely known, and there are a lot of use cases that are built on top of it. You get a lot more developers there, and the support that you can do for that particular language is much easy. How many people know Rust? Even in our organization, very handful of people know Rust. So getting a developer in Rust is very hard. You can develop it; it will be much the best version of the application, but who will maintain it? So those are all the additional aspects that you will get into, which will actually throw away any of the optimization that you talk about. It's a very 1% of the use case which actually needs this kind of a solution. All the 99 things we handle scale very well. I think recently I read a really interesting blog about why big data is dead, because very hardly databases, or very hardly there are use cases for big data. Like what is big data anymore? Because now the system has grown to a level it can handle TVs of data. There is a Postgres database which can handle tens of TVs or 15s of TVs, single instance databases. So the power of the single instance has gone to a level. So I think it's a question for a different discussion, but yeah, I will talk about it for a lot if you ask me that. But I would suggest get better at what you are doing. If you are doing at Python, get better at how, just make sure that you write the best Python code.
Okay, thank you.
Yeah, my question is, I'm not too technical, right? You moved from Postgres to Redis.
Yeah.
Because there was utilization was too high and traffic.
Yeah.
See, any database in the market, they have a load balancing and a high availability.
Yeah.
Right?
Yeah.
Whether it is NoSQL or they have a load balance.
Yes.
So what is the reason that you cannot fix the architecture of Postgres? Right, whether it's when you are all in the database so that the data is bad, or you're saying that the what was the not that one because the read itself was not.
I think there are two incidents happen. One is that we were not able to handle it at the latency that we wanted to do. That was one thing. Like someone asked, we were giving data at a late period, like 30 minutes late data or 1 hour late data, which is not acceptable. First point. The crashing bit, which happened because of the constraint enforced by the AWS. So when it peaked at the 15K IOPS which was configured by AWS, it started closing the connections. Okay, so it started closing the connections. So the connection closing started crashing the application. So that is a hardware limit that they have enforced on the RDS. We did that. We did that, and that's how we fixed it in the short time. So, but that's how the crash happened, which made us think like, is Postgres the right option for this tool? Or
Yeah, I remember you mentioning it. You said the last day was 10x.
yeah,
You did not think about okay, the 10x last day is going to happen. So the number of record thing is going to go by 10x.
yeah.
You can redesign the whole middleware database structure and into the same database.
Because we felt that Postgres is not meant for update heavy operations. Like I said, right? Postgres is not. Yeah. So we were thinking of any other thing other than Postgres, because Postgres is not good for update heavy. It is very good for write heavy because it just puts it on the append only mode. It goes back. But since it's an update, I have to delete the older records also. But if it is in memory, I have to just delete the data in memory. So that's when we were comparing all these high availability things. We were even thinking of putting in Cassandra because we already had a Cassandra cluster.
See, based upon my knowledge, right? When so in memory is like caching.
Yes.
Taking closer to the application.
Yeah.
Right. So in SD database, whenever this issue happens, we don't see the database. We insert the, for example, at Oracle, right? We don't put in the Oracle database. We use Poland at the app level also.
So we did even that. So it's a 1 year long journey where we have moved from A to B and C. So we were using Kafka and we did partition level caching, not on the Kafka side, but on the application side, we had local caching, and it's a write through cache, which makes sure that that's the way, the second step we did.
That's how you concluded that this database is.
Yes. So we moved to caching. We put the cache in between, so which reduced the IOPS by a huge number. We came from 20K to 3K IOPS from that point, because every IOPS, like every insert was happening to the in memory, and then only it was going, and the reads were fed from the cache itself. It didn't go to the actual disk or the database. So that we fixed. But then we thought like it could be done even better, and we had a very long debate. There was even a solution by AWS called in-memory DB, which provides you with the persistence and a Redis with the persistence. We compared it, we compared the cost, and then our client took a call that I'm fine with losing one message sometime in rare case, but I want to save cost. So in-memory DB is much costlier than having a simple Redis. Cool. Anything else?
Hi, Logesh, I had a question.
Yeah.
Uh, I think earlier you were talking about concurrency point. I
Yeah.
completely was not able to gather it. Could you please explain that part?
Concurrency what?
There was a slide just during which you were talking about concurrency. Like I think the second half of the presentation, if I'm not wrong.
Yeah.
I don't have the number of the slide as such.
So I think, do you want to redo the same thing I said? Because you will get this recording. If you want to know about it, you can go
Like I
through it.
didn't. The thing was, I didn't understand the scenario. Yes.
But what is your
Yes. For
specific
this
question?
point, I understood about the lock that you said,
Okay.
which we use so that we can handle multiple operations which
Okay.
happen concurrently.
Okay.
But after that, you were explaining something related to how you handled it. I think I didn't follow that.
Okay. This bit, I think I did it log free, and then these are the points on how I did it. I think we are running out of time. That's the thing. I think I
Okay.
can't explain it again. But maybe go through this
No
thing.
problem.
You can ping me on LinkedIn. I'm happy to explain to you.
Okay. Thank you.
Yeah.
Appreciate it.
Good. Thanks for that. Any other questions? Cool. Thanks everyone. Thanks for joining.